The stars that adorn our night sky hold a secret. They are powered by nuclear fusion, a process that releases unimaginable amounts of energy. This energy is what makes stars shine so brightly, and it has been fueling the cosmos for billions of years. This same process, replicated on Earth, could hold the key to a clean and limitless energy future. Imagine harnessing the power of the stars right here on our planet. Imagine a world free from fossil fuels, where our energy needs are met without depleting natural resources or harming the environment. A world where energy scarcity is a distant memory. No more reliance on oil, coal, or gas. Instead, we would have a virtually inexhaustible supply of clean energy. This is the promise of nuclear fusion. It's a vision of a future where energy is abundant and sustainable. Fusion power wouldn't produce greenhouse gases. This means it would not contribute to the warming of our planet. It wouldn't contribute to climate change. The devastating effects of global warming could be mitigated, preserving our planet for future generations. And unlike nuclear fission, it wouldn't produce long-lived radioactive waste. This makes fusion a much safer alternative to current nuclear power technologies. This makes fusion a game-changer, a potential solution to one of humanity's most pressing challenges, the need for clean, sustainable energy. The journey to harnessing fusion power is a challenging one. It requires cutting-edge technology, significant investment, and international collaboration. But the potential rewards are too great to ignore. The promise of a world powered by fusion is a powerful motivator for scientists and engineers around the globe. But the potential rewards are too great to ignore. The promise of a world powered by fusion is a powerful motivator for scientists and engineers around the globe. They envision a future where our cities are powered by clean energy, where children can play in parks free from pollution. We strive to unlock the secrets of the stars, to understand the processes that power them, and to replicate those processes here on Earth, to bring their power down to Earth. This quest is not just about energy, it's about pushing the boundaries of human knowledge and capability. The future of energy may very well lie in the heart of a star. As we continue to explore and innovate, the dream of fusion energy comes closer to reality, promising a brighter, cleaner, and more sustainable future for all. Imagine the immense pressure and heat at the core of our sun. Temperatures soar to millions of degrees, and the pressure is millions of times greater than what we experience on Earth. This environment is so extreme that it can alter the very nature of matter. These extreme conditions force tiny particles called atoms to overcome their natural repulsion and fuse together. Normally, atomic nuclei repel each other due to their positive charges, but the sun's core is so hot and dense that they collide with enough force to stick together. This process, called nuclear fusion, is the engine that drives our star. It's the same process that powers all stars in the universe, from the smallest red dwarfs to the largest blue giants. Fusion is the reason stars shine and produce energy. In the sun, hydrogen atoms, the simplest and most abundant element in the universe, are the fuel. Hydrogen is everywhere, from the vast clouds of gas in space to the water in our oceans. It's the building block of the universe. Under immense pressure, hydrogen atoms are stripped of their electrons, forming a sea of charged particles called plasma. Plasma is a state of matter where electrons are free from their atomic nuclei, creating a soup of ions and free electrons. When these plasma particles collide at high enough speeds, they fuse, creating helium and releasing tremendous energy. This energy is released in the form of light and heat, which we see and feel as sunlight. This energy, in the form of light and heat, radiates outward from the sun's core. It travels through the layers of the sun, eventually reaching the surface and then space, providing the warmth and light that sustain life on Earth. It sustains life on Earth and illuminates our solar system. Without the sun's energy, our planet would be a frozen, lifeless rock. Plants use sunlight for photosynthesis, which is the foundation of our food chain. Solar energy also drives our weather and climate. Scientists have long sought to replicate this process, to create a miniature sun here on Earth. This quest has led to the development of fusion reactors, which aim to mimic the conditions at the sun's core. These reactors use powerful magnetic fields and lasers to contain and heat plasma. If we can achieve this, we unlock a near-limitless source of clean energy. Fusion produces no greenhouse gases and only a small amount of short-lived radioactive waste. it has the potential to provide a sustainable and environmentally friendly energy source for the future. Fusion relies on abundant fuel sources like hydrogen isotopes, deuterium and tritium, found in seawater, and lithium, respectively. Deuterium can be extracted from water, and tritium can be produced from lithium. These materials are plentiful, making fusion a promising long-term energy solution. The future of fusion energy holds immense promise. If successful, it could revolutionize the way we produce and consume energy, reducing our reliance on fossil fuels and helping to combat climate change. The journey to achieve practical fusion energy is challenging, but the potential rewards are enormous. International collaboration is key to advancing fusion research. Projects like ITER, a large-scale fusion experiment in France, bring together scientists and engineers from around the world to tackle the challenges of fusion energy. Together, they are working to make the dream of fusion energy a reality. Future generations stand to benefit greatly from the success of fusion energy. It promises a sustainable and clean energy future, providing power for homes, industries, and transportation without harming our planet. The pursuit of fusion energy is a testament to human ingenuity and our commitment to a better future. Before we can create a miniature sun, we need to understand the delicate dance of atoms within a fusion reaction. The key to fusion lies in plasma, often called the fourth state of matter. Plasma forms when atoms are heated to extreme temperatures, causing electrons to be stripped away from the nuclei. This creates a swirling sea of charged particles, ions and electrons, that interact with electric and magnetic fields. Creating and controlling this superheated plasma is crucial for achieving fusion. Unlike the immense gravitational forces that confine plasma in stars, we need another approach. This is where magnetic confinement comes in. Scientists use powerful magnetic fields to contain and control the superheated plasma, preventing it from touching the reactor walls and cooling down. The most promising design for achieving this is the Tokamak, a donut-shaped device that utilizes magnetic fields to confine the plasma. Taming the beast. The challenge of high temperatures. Creating fusion reactions requires temperatures hotter than the core of the sun. The core of the sun reaches about 15 million degrees Celsius, but for fusion on Earth, we need to achieve temperatures that are several times higher. This presents an immense technological challenge. The equipment and materials used must withstand these extreme conditions without failing. To achieve fusion, we need to heat the plasma to over 100 million degrees Celsius. This is necessary to provide the energy needed for the atomic nuclei to overcome their natural repulsion and fuse together. Maintaining these extreme temperatures requires enormous amounts of energy. The energy input must be carefully controlled and sustained to keep the plasma at the required temperature. It also pushes the limits of our current materials and engineering capabilities. The materials used in the reactor must be able to withstand not only the heat but also the intense radiation and other harsh conditions. At these temperatures, no known material can withstand direct contact with the plasma. The heat is so intense that it would melt or vaporize any material almost instantly. The intense heat would instantly vaporize anything it touches. This makes it crucial to find ways to contain the plasma without it coming into direct contact with the reactor walls. This is why magnetic confinement is so critical. Magnetic fields can be used to contain the plasma, keeping it suspended in the center of the reactor. The magnetic fields act as an invisible cage, suspending the plasma within the reactor and preventing it from coming into contact with the reactor walls. This method of confinement is essential for maintaining the stability of the plasma. However, even with magnetic confinement, maintaining these extreme temperatures for sustained periods remains a significant hurdle. The plasma must be kept stable and at the required temperature for long enough to achieve a net positive energy output. The quest for fusion is a constant push to overcome these limitations and develop new technologies capable of withstanding the immense heat of a star. Researchers are continually working on new materials and methods to improve the efficiency and stability of fusion reactors. Fusion research is a global effort, with scientists and engineers from around the world collaborating to solve these challenges. International projects like ITER are at the forefront of this research, bringing together the best minds to make fusion a reality. Advanced computer simulations and modeling techniques are also playing a crucial role. These tools allow researchers to predict how different materials and designs will perform under extreme conditions, helping to guide the development of new technologies. Experimental reactors are constantly being tested and refined, Each experiment provides valuable data that helps to improve our understanding of plasma behavior and the conditions needed for sustained fusion. The ultimate goal is to develop fusion power plants that can provide a virtually limitless source of clean energy. Fusion has the potential to revolutionize the way we generate power, offering a sustainable and environmentally friendly alternative to fossil fuels. While there are still many challenges to overcome, each breakthrough brings us one step closer to making fusion energy a reality. The dedication and ingenuity of the scientists and engineers working on this problem are paving the way for a brighter, more sustainable future. A delicate balance, the quest for stable plasma. Imagine trying to hold a miniature sun in your hand. The intense heat and energy would be impossible to contain. This is the challenge of plasma stability in fusion reactors. Plasma, while electrically neutral overall, is a turbulent sea of charged particles. These particles are in constant motion, generating their own magnetic fields that can disrupt the carefully crafted confinement fields. These disruptions can lead to plasma instabilities, sudden losses of confinement that quench the fusion reaction. These instabilities are a major obstacle to achieving and maintaining sustained fusion. Scientists are constantly developing new techniques to control and mitigate these instabilities. Advanced magnets, sophisticated control systems, and a deeper understanding of plasma physics are all crucial for achieving the delicate balance needed for stable plasma confinement. The quest for stable plasma is an ongoing battle, a delicate dance between control and chaos.